So now I want to talk a little bit about angles. In this case, we're looking at the direction angles that we solved for in that last problem. We got theta x to be 105.5, we got theta y to be 122.3, and we got theta z to be 36.7. We talked about the three different kinds of checks: the magnitude check, the UV, the unit vector check, and the visual check. Can you see that this is, remember when we solved for unit vectors, we're really finding the cosine of theta xi plus the cosine of theta y plus the cosine of theta z, right? So, and then there are times that we find the unit vector, so this is when we are given angles. When we're given the distances and we're looking at ratios, the unit vector turns out to be whatever the distance is in the x over the total distance, I, plus y, the distance in the y over the total distance. I'm putting a bar, this shouldn't be here. And then j, plus the z distance over the total. So let's say distance, distance, distance. Okay. You could see that this is really the same as this. These are both the unit vector in the x. These are the unit vector in the y. And this, I forgot to put a k there. Oh, that doesn't work. And this represents our unit vector in the z. We did a unit vector check by taking these values and squaring it. Wouldn't the same unit vector check using the direction angles be the inverse cosine, the cosine squared of theta x plus the cosine squared of theta y plus the cosine squared of theta z? And what should that come out to be? 1. Because the magnitude of the unit vector turns out to be 1. So just look at that for a minute. So when we do a unit vector check, we could either check it in terms of the distances, or we could check it in terms of the direction angles. And you'll see that on the homework. I'll ask you to do one or the other. Okay? All right, so now I want to go talk a little bit more about angles. So I'm going to erase this right now. So far in components, we did a 2D, that one didn't work. We did a 2D angle problem on the first video, and we did a 2D ratio problem on the first video. And then the second video, we did a 3D ratio problem. So now we have to do a 3D angle problem. And in order to do that, I want to make sure that you understand a little bit more of the use of the cosine. So let's go back to this. We have a 2D problem. This is the x and y axis. Here's my force. And if this is my force, then what does this angle represent? Yeah, theta x. And what does this angle represent? Theta y. And we find that the force in the x is equal to F times the cosine of theta x, and Fy is equal to F times the cosine of theta y. What if it was a 3D problem? If it was a 3D problem and you were given theta x, theta y, and theta z, they were all given, how would you solve for fx, fy, and fz? It would really be the same as what you did in the 2D problem, right? It would just be carried through. Fx is f times the cosine of theta x, fy is the f times the cosine of theta y, and fz is f times the cosine of theta z. So let's talk about why this is the case. It was something you learned in math, dot product. When was that? Was it at 5B, math 5B, 5A? I'm not quite sure. But if we had two vectors, and we wanted vector A and vector B, and we wanted to dot those vectors, do you remember how we did it? There were two different ways. One is you say the x component, sorry, can't use small values now. The x component of A times the x component of B plus the y components times each other plus the z components times each other. Remember getting that? And what is the dot product? This turns out to be a scalar value, right? And how is a scalar different than a vector? A scalar only has a magnitude. Magnitude only. No direction. And there was another way to find these two. You remember when you wanted to dot these two? If you didn't know what the components were? You took the magnitude of A, and this is my representation of the magnitude. The magnitude of A times the magnitude of B times the cosine of the angle between them. Do you remember that? Let's take a look at, let's compare this. Let's compare this to what's going on here. This is a vector, it's a force going in a certain direction. And this is a vector too, but if we consider it a unit vector, it has a magnitude of 1. So if I dot the force with the unit vector along the, let's do this, along the x-axis, wouldn't it be the magnitude of the force times the magnitude of the unit vector, let's call this x-axis, x-axis, times the cosine of the angle between, based on the dot product. If I dot two vectors with each other, I take the magnitude of the first times the magnitude of the second times the cosine of the angle between. Here, I'm dotting this force with the unit vector along the x-axis, and I take this value. What is the magnitude of the unit vector equal? 1. And what does the angle between them represent? Theta x. Don't I then get this? The force in the x is equal to F times the cosine of theta x. I found when I was a student in math that I learned how to solve the problems, but I didn't necessarily know what they meant. You all had different teachers, and maybe it's different, but what I think is great about engineering is you learn the concepts in math and maybe even physics, but you don't necessarily what they mean, but when you get to engineering, that's where you learn what it all means, especially when we're talking about math. So you learn the dot product, you learn how to solve for the dot product, but maybe you didn't learn what it means, and now you know what it means. Basically, if you take a force, if you dot, let's say, if you dot a force with a unit vector, you get the component of the force in the direction of the unit vector. So I dotted a force with the unit vector, and I was able to find the component of that force in the direction of that unit vector. In the previous video, when we talked about 2D and 2D angles and 2D ratio problems, one of the things I talked about is in engineering, we tend to use cosine. And a reason I mentioned earlier, the reason why is because it always gives you the correct sign, as long as you're taking the cosine of the direction angle. But the main reason that we use cosine is when you're finding components of forces, you're really using the dot product, and the dot product involves the cosine function, not the sine function. So whenever you find components, you're basically using the dot product. So that's another reason that we tend to use cosine more. Okay, so now moving into 3D, if you're given theta x, theta y, and theta z, you could find the components of those three forces by multiplying the force times the cosine of the direction angle. And it's based on what our dot product is. Okay, now we're going to do a problem. The problem we're going to look at is in the packet that's on the website. And the problem is on page It's on page 4, I believe. I gotta find it. I separated it out into different pages so I had more room. But for you guys, I think it's on page 4. So go to page 4 or 5. The problem is on, it is a 3D problem. That's an angle problem. And I guess I should probably draw it up on the board. See if I have a clean copy of it. Okay, let me erase this. I'll stop the tape and draw it up there.